It's nothing but tan inverse of y by x or x by y. So we have two parameters, beta and alpha. So tan inverse of y by x. So you can easily calculate what is the rotating angle of the rotor. So that angle has to be fed here because we need to rotate all these blocks to synchronize with the speed of the rotor. So this is a natural formula. There will be an angle is required in these blocks. And these are some of numerical results shows how these control algorithms are working. So initially, this is the reference value, what we feed here. The reference value, what we feed here is reference value is feed here is shown here, the omega r. The omega r is the reference value which is fed from the block here. So this value is shown here. So initially it starts with 0 time to the maximum speed. We can't keep 1. All are shown in per unit value. So I can't keep 1500 RPM because induction motor never runs at 1500 RPM. So less than that, say 1450 RPM, it can be equivalent to 0.8 or 0.85. So 0 to 0.85. This is the actual speed of your rotor, which follows the reference value. So initially we started from 0 time, maximum speed. Then after about 4 seconds, it has been reduced to 0. You can see the speed tracks the exact reference with um, with a normal speed control, with having a transient, and of course it has a uh, not a peak overshoots, and steady state is very normal. I mean, there is no any huge oscillation is observed, very smooth. This is because of only PI regulator. Then this shows you the value of your ID. We are talking about what happened here, ID, IQ. So initially the machine start at the speed 0, the maximum speed. So the current reaches very high value because when you apply a voltage or a voltage to your stationary object with a full value, it has to take a huge current, then it comes back to your normal value. So technically we call it as a kickback effect. So after a transient period comes to 0 because we kept the flux producing component as 0. Then we have IQ. IQ is the torque producing component. So the torque producing components we are having at around time 0. We are going to have a full speed, so that obviously torque also increase to the maximum. Then the machine is not loaded, so come to almost near to the no load requirement of the current for the no load torque. Then we are reversing the speed here to 0, so that there is a reversal, then backs to the nearly no load requirement for the current. And this is the rotor flux. So rotor flux linkage is kept exactly 1, the maximum value. So this is the reference value, and this is the actual value which is generated from the electrical machine. And about load, you can have a look. This is a variation. We have the variation exactly from 2 to 6 because initially the machine starts at about initially the machine starts with maximum speed, obviously. Then it takes around time to stabilize around 2.5. That's why you can have a look. Initially the load is 0 and the no load is 0. So obviously the machine takes to the maximum value of the speed. We have the maximum load. Then again backs to 0. Obviously the same response. It's because of this characteristics. And this is due to the voltage which is having the peaks, because in the beginning we start at the maximum speed, then there is a reversal to 0 suddenly, so that you have two peaks exactly due to these behaviors. So what happened to direct and indirect vector control? In this case, we need to have a state space model. If you know the control system, so we need to have a state space model of your complete induction motor to have a control either directly or indirectly. So that the most important is you should know the dynamics of the machine, its complete theoretical equations, and of course we can technique called as an observer. We can make an observer which is equivalent to your same dynamics of your motor. And in this case, both stator direct and indirect vector control, the stator current is measured directly. You put a sensor, you measure all the currents. For the indirect vector control, the machine magnetic field is Usually, we can calculate by keeping a sensor in the air gap, which is the most complex technique, so that we don't go for this one unless it's a very specified or a specific application. We are using this technique to keep a sensor in the air gap, which is between the rotor and stator. This is the most complex technique. And about indirect vector control, we can use a machine flux method where you can have a unique model which is equivalent to calculate your flux of your machine, and then you can able to do the control algorithm. So these are the various possibilities of direct and direct vector control. How to calculate the flux? That's most important. We have two different methods. We can go for the first method, which is a state space method, where all the parameters will be sinusoidal in behavior as like a machine as a sinusoidal distributed winding on the stator. So it's a behavior we calculate all in the parameters of sinusoidal. And the model which you develop will be kept as an open loop model, and the behavior will be same as a real-time motor. So we use a model, you generate a model which behaves exactly as like a real-time motor which is in application which you choose. Other possibility, we can have an adaptive observer. This is another trend in controlling an induction motor. In this case, again, we make an open loop model, and the model will be able to control the induction motor in real time, as like we can able to control very robustly various parameters. And this is very complex model. I mean, the developments with the theoretical equation to have a more precision. And most important is we should be able to know about the rotor and stator flux methods. I mean the parameters. How it looks, a simple idea, more simple. We can have a stator flux reference, and the feedback can be taken from the open loop model. What is this open loop model? The exact replica of a induction motor in real time. We are modeling a induction motor with a theoretical equation to have the similar behavior in real time to your numerical equations. That's most important. So it all depends. This control always depends on how you are making this open loop model. What is the input? Only the stator current and the voltage are the two inputs to the model. From the model, we are going to calculate rotor speed and also stator flux. And these two parameters are output of these block, of course, the angle of rotation from the rotor. Then the control algorithm is very simple because we are going to control both reference value of stator flux and feedback value, reference value of your speed, and of course the feedback from the open loop model. Then these two parameters are given to the PI regulator. So the PI regulator will try to keep omega r, reference speed, and reference flux. From this, we are able to calculate what is the current required for the stator winding. So I already said in case of these vector controls, the most important to control stator very easily. And from this, again, we have the real value of stator current, which is compared here and given to a transformation block. So from the transformation variables, we can able to get a voltage parameter, which can able to control your inverter. So in terms of current, because two feedbacks are the current error is given to the block, and it calculates the reference value of your current, which controls the PWM. So then it's given to a PA regulator, which able to generate the modulating signal, or I can say the control signals, which going to control the 6 PWMs of your inverter. Then you can have a dynamic control of your induction motor, where you can control flux separately and speed separately. The last method is a very complex method where we can avoid field weakening, because most important is the field weakening region. We can have in a closed loop control, you can lose the field. Field means magnet flux. So in this way, we can able to control an effective control by adapting some small changes with the previous algorithm I discussed. So you can have a speed reference and the feedback is calculated. This block I already explained, so I don't want to give you more inputs. So omega is taken from the calculation. Similarly, start from here. Omega r is the reference of your rotor flux, and omega r is the feedback value which you have calculated from the information of the current. And these are fed to the PI regulator. So the PI regulator can help you to find the reference value for torque, of course, for the flux. And these parameters are compared with the actual value from your calculations. So these are the feedback values. Again, you put a PI regulator. These PI regulator will control the current of the flux, so torque, the current of your flux. So input are the current. So obviously you will get a voltage parameter. So here you are going to have a voltage parameter of your torque, reference, and the voltage parameter of your flux producing component, and these are given to a